So for the first topic today, we're just learning about some notation of functions. And we say the letter F, starting from a set A, which is called the domain, going to a set B, which is called the codomain, is a function if it satisfies certain properties. Hold on, let me make sure. Okay, good. So the codomain is not the same as the range. So the set B is the set where it's going towards, not necessarily the range, it's like the lowest to the highest. So let's just give a quick example. So let's say the domain and range are both real numbers. So let's do an example. So F goes from real numbers to the real numbers. And you can define F, for example, by a formula. Let's just say F of X equals X squared. So the domain is always the full set A. So the notation F goes from A to B implies that every number that's in the set A can be plugged into the function. But it does not imply that every number in the set B can come out of the function, though. So can anybody give me an example of a number that's, think of an example that's in set B, which is in the codomain, but you cannot get that number from F of X. You cannot get that value from F of X. So what? No, you could get one by plugging one into the function, you get F of 1 equals 1 squared, which would be 1. So one is in the codomain, but and you can't get it from F of X. Can anybody give me another example that you cannot get from F of X, as assuming F of X equals X squared? So one is in the codomain, and since F of 1 equals 1 squared, which equals 1, you can get that number in the codomain from the function. 40? No, that's still, you can still get 40 from it. Because if you plug in the square root of 40, 0, you can get 0 from it as well.
You get 0?
If you put in 0, you'll get 0 squared, which is 0.
It's just any negative number?
Yeah, any negative number. So, for example, -1 is in R. But F of X does not ever equal -1 for all numbers X that are elements of the domain. So for every number that's in the domain, for every single number in all of real numbers, there's for whatever number you pick, it's never true that F of X would equal -1. Because when you square any real number, you get either 0 or a positive number. So -1 is an example that's in the codomain, but it's not, doesn't come from that function. So therefore, what's the range of the function? So since the codomain is not necessarily the range, how do you define the range? So the range is, or they also call this the image. The range, which is also called AKA image of the function f, is the set of all y values such that y is equal to the value of the function f where x is an element of the domain. So it's a set of any y value such that y equals the value of the function for any element in the domain. So now notice that it's a little bit of confusing of a definition. So sometimes they actually say this. They define the image of one point at a time, like this. So if x is in the domain A, then what? What do we know then? We know that the value of the function f of x is contained within the set B, right? So they call f of x is called the image is called the image. The image of x under f. So this actually is a strange way of thinking because this sort of makes you think of functions as translations. So imagine if you had a word in English that was called x, and you had a translator that translated it into German, and that function f did that. So the f of x would be like the German word. It would be called the image of x or the word for x under the function f. So it's kind of like the German word for the same word in English. And if you translated all the words that way, then you just get, if you just took f and you plugged in the entire set A like that, that would be called the image of A under f. Does anybody remember what this is actually doing? Image of the whole set, the whole domain under f. You obviously can't plug a set into the function because the function only allows you to plug a real number into it. So remember that word that I used like last class started with an O? What are we doing? We are overloading the operator of the function notation, right? So you take an operator that's not actually defined for something and you just pretend like it is. Now, of course, in a computer programming language, you can't do that unless the programming language has been actually pre-programmed to let you do that. But a lot of times in math, they do things like that, and they just define it in a weird way. So f of A is called the image of A under f. And of course, you can't plug a set into a function because you can't take a set and square the set, right? Like you can't take the set A and do A squared. But they still define this set f of A is just called the same thing as was before. It's just a set of all values y such that y is equal to f of x for some x that's in the domain A. So it really means the exact same thing that we talked about before. But now you have a shorter notation for it. So what is the image? What is the image of the set A of the domain if the function is equal to x squared? Well, what's the image of this of the set of real numbers if the function is equal to x squared? Just make sure you understand this concretely. So that means if you plug in all real numbers into that are elements of the real numbers into the function x squared, what set would you get out? So you kind of already know because you've already thought about it. What numbers would you not get out? She already said it. Negative numbers. So you could get out any other number, right? So you could get out all numbers that are 0 to infinity. So the image of that function would be the interval from 0 to infinity, including 0. Okay, then what if you worked backwards, though? Okay, now let me actually put in a quick comment, actually. What set is a function itself a subset of? So the function f is actually a set. It's a subset of what set? What set is a function a subset of? Well, one way to think of a function is it's an ordered pair. So basically, you could actually say a function, this is a little bit abstract, but a function is actually equal to a set of values a and b, right? Such that a is in the set A and b is in the set B, right? Now that actually gives you a hint, because what set was defined as all possible values from one set in the first coordinate and all possible values in the second coordinate were from another set. That's called the Cartesian product of sets, right? So every function is a subset of all possible of the whole set of Cartesian products of A and B. Except there's one more qualification that makes something be a function besides just that A is an A and B is an B. Because if that's all a function were, then it would be nothing different from the Cartesian product of A and B. What else has to be true in order for it to be a function? There has to be some formula such that f of A equals B, right? So it's a subset of all possible values. Okay, I made a mistake. My fault. Hold on. I'm going to say A cross B. The Cartesian product is called A cross B. So every function is a subset of the Cartesian product A and B. That just means its x values are part of A, its y values are part of B, and the relationship between the x values and the y values are that there's a formula. So if you plug in the x value of A, you'll get the y value of B. Now yes?
Just straight X.
What?
Sign.
No, it's just straight x. It's just a regular x, but it's not the variable x. It's just an x. It basically just means x times b. But once again, it's not the multiplication times. It's like the operator has been overloaded to mean something different. That's not actually multiplication. So you'll notice math is actually kind of ambiguous. Everybody always talks about how math is perfect, but actually many things in math are overloaded depending on what the things beside them actually are. So if these are sets, this is a set and this is a set, then A times B does not mean like literally like 1 times 3. It doesn't mean multiplication. It means Cartesian product. So every function is part of like a subset of the Cartesian product of the sets A and B. Okay, perfect. What about the pre-image of B? So let's say if I had a function that translated English to German, and if I put in an English word into it, I would get the German word on the other side. So assuming that there's one German word that would mean the same as every one English word. So let's say I'd have a function that went from English to German like that, and I've misspelled German in the top part, sorry. So what's the image of an English word? What is f of an English word? And the image is a German word, right? So what's the pre-image? Pre-image of a German word. Of a German word would be equal to the English word, right? So pre-image just means if you translate it backwards. So basically, if f of x equals y, then x is called the pre-image of y. The pre-image of y. And y itself is called the image of x. So in a way, you have to think of functions as basically the thing itself is still the same identity, same meaning or whatever. But the value of the function just puts that meaning into the set B, like the German language, for example. And the x value is like the same meaning, but in the English language. So if you think about functions this way, it's a more powerful way of thinking about it because the concept of what you're plugging into it maybe still has the same meaning the whole way through. Like the word itself is still the same word, but you're just translating it from one set into another set, or from one nation to another nation, or from one language to another language. All right, so let's find another vocabulary word. Injection. So it's not like a medical injection. Injection means a one-to-one function. So one-to-one function means that if f of A is the same as f of B, that implies that A equals B. So if it's true that f of A equals f of B implies A equals B for all A and B, if that's means it's true for all A and B, then it's an injection. So can anybody give me an example of a function that's not an injection? Can anybody think of a function that equals the same thing when what you plug into it is not the same? What about something that you can factor, like a quadratic equation? If you have a quadratic equation, you can always find two solutions that are always equal to the same number on the other side, right? So let's just try this one. Let's say x squared minus 5x plus 6. Let's say that's the quadratic function. And can anybody factor that? How do you factor x squared minus 5x plus 6?
This is like old algebra.
Yeah, this is like old algebra. So split up the x squared into x minus x. Now, if you know this trick, you can also bring down this first sign, the first negative sign. Multiply the signs together, negative times positive is a negative. So that means both signs are negative. And then you break apart the 6 into 6 times 1 or 2 times 3. Pick the pair that if you put them in the blank spaces, it'll add up to -5. Well, in this case, if I pick the 2 and the 3, it'll already have a negative sign in front of both of them, and so that will add up to -5. So that means that the solution is 3 and 2, right? So f of 3 equals f of 2, because those are both the solutions to the equation. However, though, is it true that 3 equals 2? No. So 3 does not actually equal 2, so this is not an injection. Because anything that has the same value of the function, when you do not have the same value of input, that's not an injection. It's not one-to-one. All right, let's think about the next topic, which is called onto. So by the way, function that is an injection is called injective. So injective. Injective, that's the adjective. Injective is the adjective form of it. Injective is injective function. Injective functions are functions which are one to one. Injective functions are functions which are one to one. Okay, so let's learn the next, kind of like the opposite of that. Surjective. So surjective functions are functions which cover the full codomain. So what does he mean by cover the full codomain? That means that for all values B that are part of this codomain capital B, for all values B in capital B, there always exists a value of A in the domain, or always exists a value of A within the domain, such that, by the way, the word such that is another common symbol. It's actually like the element symbol, except it's written backwards though. Such that. So for all values that are in the codomain called B, there exists one value A that's within this domain A, such that f of A is equal to B. So that's basically just saying that this is not a function like x squared. So remember when we did the example of x squared? Remember when we did the example of x squared? We found x squared did not cover the full codomain because, like, for example, -1 is a number within the codomain of real numbers, but the function does not ever equal -1. So the function x squared, if you look at this set of real numbers, the function x squared only covers part of that graph. It only covers the part above 0, right? It's like a parabola that goes up, but it does not cover the bottom half of the graph, right? So a function that's onto, well, I didn't say the word onto yet, but a function that is surjective covers the full graph from bottom to top and everything in between. So a surjective function, it's also called onto because a surjective function, function's graph goes onto the full codomain. So basically, AKA, what does that mean? That just means that you could also say this is called the codomain equals the actual range. So in general, the codomain does not equal the range of a function. The range of a function might not cover the full graph. But if the codomain does equal the full graph, then the codomain equals the range, and that's called onto. So can anybody give me an example of a function from real numbers to real numbers that's onto? I'll give you a hint. Think of a polynomial that goes from negative infinity to positive infinity. Any odd degree polynomial would do that, right? So like if I just said the simplest one would just be f of x equals x. That has a power of 1. And the graph of f of x equals x looks like a diagonal line, right? So for one thing, that one is onto because the graph covers the full y-axis, right? It goes from negative infinity to positive infinity. It goes onto the entire codomain y. So basically, the range of it equals the full real numbers. Does this function happen to be? Is it surjective? Well, it is surjective, but is it also one-to-one as well? Is there any time when you have the same value of x from f of x equals x? I mean, is there any time when you have the same value of okay, well, this is x, but is there any time you have the same value of y this says x, but pretend like it's y? Is there any time you get the same value of y from the function, but you have two different values of x plugged inside of it? Like 3 and 5 or something? No, because if you had two very different values plugged inside of the x, well, since f of x equals x, you'd also get two different values out, right? So anytime you plug two different values in, you always get two different values out. So that means it's impossible to plug two different values in and get the same value out. So this is also one-to-one. So this function is one-to-one, and it's also onto. So this function is onto, and it's also one-to-one. So can anybody think of a function that's one-to-one? Can anybody think of a function that is onto, but it's not one-to-one? Can anybody think of a function that's domain, that's range is negative infinity to infinity? Doesn't have any jumps or holes, but it covers the full graph. So it covers everything and it's onto the whole number line. But however, though, but it's not one-to-one. Good morning. Well, we would have to have some twists in it, right? Some sort of twists. So what about if we did a function like this? I know that if you start with an odd power, like x to the fifth power, that it would go from negative infinity on the left to positive infinity on the right. But then what if I added in some like negative stuff after that, like negative 16x plus 8, for example? Let's just see if that adds some twists and turns. So let's look at the graph of that on the great and powerful website called desmos.com/calculator. And x to the fifth. So if you're on the video, I'm just going to desmos.com/calculator and plugging in x to the fifth minus 16x plus 8. So sure enough, we get something that looks like this. It goes up, then down, then back up. So at the end of it, it still goes from negative infinity to infinity. So it still goes onto the full y values. From the y values range from negative infinity to positive infinity. However, though, so I know it's onto it. That function goes onto the full set of real numbers. So it goes onto the full codomain. So in other words, its range is equal to its codomain. Because this function f goes from real numbers to real numbers, right? But is it one-to-one though? Well, I don't know exactly what they are, but I know it's not one-to-one though, because for example, this point and this point and this point are all the same y values, right? So I'd have to use algebra to find them for sure, but I know just looking at the picture of it that there's three different values like A, B, and C. And obviously A does not equal B, which does not equal C. But f of A does equal f of B, which does equal f of C. So anytime it does not pass the horizontal line test, so if a horizontal line goes through the graph of the function more than once, then it's not one-to-one. So this is not one-to-one because it does not pass the horizontal line test. So horizontal line going through the function crosses it more than once. That's called the horizontal line test. Just like the vertical line test you learned a long time ago was if a vertical line goes through a function more than once, it's not a function at all. And if horizontal line goes through a function more than once, then it's not a one-to-one function. So once again, there's the picture of the graph on desmos.com/calculator. Okay, perfect. Now, let me go back and relate this to cardinality. You ready for that? So cardinality. Who remembers what cardinality means? Cardinality. So let me just review real quick. What does that symbol mean? And what's the value of it? If I write that down, what does that mean?
Set of numbers.
Yep, it's a set of numbers, and what do the lines around it mean? The cardinality of that set. And what is the cardinality defined to be? The number of what? The number of things in that set. So what's that? What is that equal to? 3, right. So the cardinality of the sets is the same. So here's a rule for you. Cardinality of sets is the same if there exists a bijection between them. What is a bijection? A bijection is just a strange word. It's a conjunction of both injection and surjection. So any function that is both an injection and it's also a surjection is called a bijection. So we've already seen an example of a bijection. F of x equals x. That's actually a bijection. So the cardinality of 1, 2, 3 is 3. What's the cardinality of 1, 2, 3, 4? It'd be 4, right? So here's the mysterious question I want to ask you today. Which set has more numbers in it? The set from 0 to 1 or the set from 0 to 2? The closed interval of real numbers. Sorry, the closed interval of real numbers from 0 to 1 or the closed interval from 0 to 2. Which set has more numbers? Or if one set doesn't have more numbers, then they would have both have the same number of numbers in them. Or do they have exactly the same number of numbers? So first, this question really confused me. Because obviously, if you took the number of numbers between 0 to 1, you could include another number, like for example, 2. This set would have to contain at least one more number than this set does, right? Do you agree with that, at least at first? It'd have to contain at least one more number than the other set does. Except that question brings into another question up though. If you have the number infinity, if you add 1 to infinity, does that actually make infinity bigger, or is it still just the same amount of bigness?
Same amount.
The same amount. Now, it is true though that sometimes some things like rational numbers, there can be an infinite number of rational numbers and an infinite number of irrational numbers, but you can still never get an irrational number from a rational number, right? You can get very close to them. Like you can get a decimal value that's within 32 decimal places of pi, but it's never ever going to be exactly pi, right? So you can get close, but you can't ever get exactly. So the question is, does this set really actually have more numbers, like in the sense that maybe there's more the irrational numbers can be different from rational numbers, or does it really have the exact same number of numbers as that? Well, the question is, it all depends on whether or not that rule is true, what we just said above, that whether there can exist a bijection between them. So if there's a bijection between two sets, that means for every unique element of this set, there's always a unique element of that set. And for every unique element of that set, there's also a unique element of this set, because it's one-to-one in both directions. Bijections basically mean it's one-to-one in both directions. So can anybody think of a function that starts from 0 to 1 and goes from 0 to 2 and is one-to-one? So we want to think of a function starts from 0 to 1 and goes to the set 0 to 2. Well, what about this? What if I just said f of x is equal to 2x? So let's think about this. Is the function f of x equals to 2x, is it surjective? Let's think about that first. Is it surjective? I shouldn't use the word it because that's ambiguous, so I should say is f surjective? So does it cover the full set 0 to 2? Yeah, because if I plug in all the numbers from 0 to 1 and multiply them by 2, you get all the numbers from 0 to 2 without missing any, right? Now, the way to prove something is surjective, the book is a little bit picky about this. To prove something is surjective, you have to let there be a value, I'll just call it B, that's an element from 0 to 2, and you have to find that there exists a value A such that f of A would equal B. So we need to find a value of A that's between 0 to 1. And I'm going to write that strange word again. That means such that. We need to find an A value that's from 0 to 1 such that f of A would equal B. But how do I write the word such that with symbols? It's the same as the element symbol, but it's just written backwards a little bit bigger. So I'm going to say like this. So we need to find A that's between 0 to 1 such that f of A would equal B. I'll let you, since you have very brilliant minds, I'll let you try to think of a value of A so that f of A would equal B. Can anybody think of what it would be? What it could possibly be? So can you think of a number A that's between 0 to 1 such that f of A would equal B?
2.
2 something? 2B? Or not to be? That is the question. So in this case, 0. Well, in this case, your one is on one extreme, one's on the other extreme. How about something a little bit between 0 and 2B?
1.5. Okay.
So you need a number such that if you plugged A into, so what is f of A? F of A would equal 2A, right? So f of A equals B is equivalent to saying that, what is f of A again? It'd be 2A, right? F of A, whoops, sorry. F of A is equal to 2A, right? So it's equivalent to saying that 2A equals B. And 2A equals B is equivalent to saying what? By the way, I'm writing equivalent means if and only if. And when you're doing logical things, you can reduce any argument with the statement if and only if to another argument without weakening the argument of any of the steps. So f of A equals B implies that 2A it not implies actually, it's equivalent to 2A equals B, which is equivalent to A equals 1/2 B, right? So the question is 1/2 B between 0 to 1? Yes, because B is from 0 to 2, so half of that would be from 0 to 1. So we found an A, so we can just say let A equal 1/2 B. Then f of A would equal 2A, which would equal 2 times 1/2 B, which would equal what? Which would equal B, right? So we've proved that there is an element between 0 to 1, we found it, such that f of A is equal to B. So we've proved that it's surjective. And we only need to prove it's injective. How do we prove that it's injective? Well, to prove it's injective, we just remember that if you have the statement f of A equals f of B, you need to be able to prove that that implies that A equals B. So let's just pick two numbers. If f of A equals f of B is equivalent to saying that 2A equals 2B, because remember f of x equals 2x. So f of A equals f of B is equivalent to saying that 2A equals 2B. And if you divide both sides by 2, that's equivalent to saying that A equals B. So f of A equals f of B is equivalent to saying that A equals B. However, though, the definition of injective is that if f of A equals f of B, then A equals B. We've actually proven an even stronger case. We've proven that if f of A equals B, that if and only if that happens, that you'll have 2A equals 2B, and if and only if that happens, A equals B. So we only needed to prove it in one direction in order to prove that it was injective. We've actually proven it in both directions, so we've definitely proven that it's injective, right? So it is injective, and if something is injective, so this implies that it's injective. And if something's injective, that means and if it's injective and if it's also, we've proven that it's onto, what does it mean if something's onto well, I should use the word surjective. Something's surjective and injective, what is it called? Bijective. Bijective, exactly. And if it's bijective, if there exists a bijection between two sets, that means there have to be the exact same number of elements within each set. So that actually means there's the same exact number of numbers between 0 to 1 as there are from 0 to 2, which is weird. And I stopped believing that in math when I first heard that in my class like this, but then after all, it made sense because the thing is, real numbers are basically just kind of like a squishy. Have you ever had like a stress ball that you can like squeeze or whatever, like a rubber ball? Are the molecules in that ball the same number of molecules if you squeeze it to be smaller? So real numbers are basically just sort of like a squishy rubber ball. And if you just multiply them each by a half, you get the numbers from 0 to 1. If you double the numbers from 0 to 1, you get the same set of numbers, but you just get numbers from 0 to 2. So you're basically taking the same infinite number of numbers and just squishing it to get these numbers and expanding it to get those numbers. So it only works because there's an infinite number of numbers. If there weren't an infinite number of numbers, then you'd obviously have more numbers between 0 to 2 than you would from 0 to 1. So the real numbers themselves are basically kind of like a squishy rubber ball that you can squish to be small or stretch out to be bigger. There's the same number of them no matter how wide your interval actually is. As long as you have at least an infinite number of real numbers continuously in the interval. So for example, if you have this interval 1 to 1, how many real numbers are in that interval from 1 to 1? Just 1, right? So that's not an infinite interval. Okay, well then your homework is going to be page 162. Homework is page 162, number 22. Page 162, number 22. And that says to determine whether each of the functions is a bijection from R to R. So we have a few minutes left. So just to give you an example, I'm going to talk a little bit about number 23. 23 says 2x plus 1. Let's just do maybe part A from 23. So you have to do number 22 on page 162 and decide if those functions are bijections or not. But together though, let's just look at part A from number 23. Is this function a bijection from real numbers to real numbers? Well, how do you tell if this is a bijection or not? You have to, first of all, tell whether it's onto, right? So is the function f of x equals 2x plus 1, is it onto all real numbers or not? So if you looked at the graph of that, would it go fully across all possible y values?
Yeah.
Yes, so it does because the graph, the range or whatever, the range equals minus infinity to infinity. Is it 1 to 1? Is the graph of 2x plus 1 1 to 1? So in other words, if f of b equals f of a, does that imply that b always equals a? Well, we might actually have to do this in like a proof. So let's just assume that f of b equals f of a. Well, that's true if and only if, what's the value of f of b? It'd be 2b plus 1, right? What's the value of f of a? It'd be 2a plus 1. So f of b equals f of a implies that 2b plus 1 is equal to 2a plus 1. Subtract 1 from both sides. That would be equivalent to saying that 2b equals 2a. Once again, that's equivalent to saying that a equals b. So the statement that a equals b can be derived from the statement f of b equals f of a. So anytime that the statement f of a equals f of b implies the statement a equals b, that implies that f is 1 to 1. So if this statement cannot be implied from If this statement is not the result of that statement, then that means it's probably not one-to-one. It's actually easier to prove something is not one-to-one though, because all you have to do is find one counterexample that proves it's not one-to-one. So that is. Let me actually do one more. Let me do a counterexample. So x squared plus 1 equals f of x. That's part B of 23. So part B, that one is not one-to-one. So I'm going to show you how to find a counterexample. Can anybody think of a counterexample that proves that that's not one-to-one? Well, what about 1 and -1? So f of 1 equals f of -1, right? Because 1 squared plus 1 is equal to 2. -1 squared plus 1 is also equal to 2, right? So f of a equals f of b, but a does not equal b, right? So when f of a equals f of b, but a does not equal b, that proves it's not one-to-one. And if it's not one-to-one, then it can't be a bijection. So if it's not one-to-one, that's enough to prove that it's not a bijection. So there's an example of how to find a counterexample as well as how to find a proof of one. So you can work on that one problem, turn that in on Wednesday, when you come to class on Wednesday at 9 a.m. So good luck, everybody, and then we'll keep talking about more of this math next time. We have some really exciting things to learn about next time, by the way.
Have a good day.
You too, thank you very much. See you later. Oh, by the way, did I get the late people sign in? Was that Logan?
I just email you the stuff that was doing today, like just do it.